Last week we covered rectangular or Cartesian complex numbers. So this week we're going to do complex numbers in polar form. Yeah, so we're going to look at how we represent them in polar form, multiplication, division, use of calculator to convert between the two forms, and addition and subtraction of polar complex numbers. Alright, so we have the two representations. Last week we looked at this rectangular representation over here, the J complex numbers, J representing imaginary axis and representing square root of -1. This week we're going to look at how we can represent the same vectors in polar form where there's a magnitude and an angle from 0. Okay. So, if we let a complex number z be represented by the complex number x plus yj, as shown in the diagram, so we've gone x across the real axis and j times y up the imaginary axis. Yeah. We then let the distance O to z equal little r, okay, and the angle OZ makes with that to be theta. Then we could use Pythagoras' theorem on the real part and the imaginary part to find the length of that hypotenuse line we've called r. R is called the modulus mathematically, or what I tend to use as the magnitude. So we're into physical quantities of the vector, and z that's written as formally z with two horizontal bars either side, meaning just the magnitude of that vector. Alright. Sometimes certain problems we might only be interested in the magnitude and be ignoring the angles. Just depends on what we're doing. Okay, and then using trigonometry and the tangent ratio, because the rectangular form gives me opposite and adjacent sides to the angle, rearrange that and I can find the angle theta from tan to the -1 of y over x, opposite over adjacent. And the full form of the complex number in polar form, z is equal to the magnitude at an angle theta. Okay, so the units, and if there's units, so if we were talking about z as an impedance, that would be the magnitude ohms angle, whatever the, if that was 6 degrees like that. So your units go between the magnitude and the argument. Right? So let's have a look at a problem then. Determine the modulus and argument of a complex number z is equal to 2 plus 3j and express it in polar form. Okay, so we're 2 on the real axis and 3 on the imaginary axis. So we can find r by square root of 3 squared plus 2 squared. minus root of 13, which is, check these please, 3.606 for significant figures. Yep. And then the angle is equal to tan to the minus 1 of opposite, which is 3 over 2, and that equals 56.31 degrees. Therefore, polar form of 2 plus J3 equals 3.606 angle 56.31 degrees. All follow that? Doesn't all speak at once. Right. So equally, those angles, the angles could be in radians. Alright, so there's a topic that we're going to start soon called calculus, and in calculus you can only ever work with the sine and cosine functions if your angles are in radians. A lot of work we do in electrical will have your frequency in omega form, and again you'll be in radians. So we just need to make sure, if it's asked in a specific form, that you've got your calculator in the right form. And that goes for when you're doing the conversions that we'll do shortly as well. Alright. So that's how we do that. So have a go at those ones. Yeah. What you need to think about here carefully is remember we're looking for the angle, positive or negative, from 0. So you need to think about what quadrant it's in, because when you find the angle for this over here, you're going to find that angle. What you actually want is that angle in there. So you've got to take that angle off 180 degrees to find it. And then when we go this way, we want negative angles. You'll see that. That one is going to come in that quadrant because it's got a negative real part. Yeah. So you'll be finding this angle in here, and then you'll need to take it away from 180 to get this angle in there is what you're looking for. Right? That one, yeah? So tan to the minus 1, 4 over 3. That's it, yeah. It's okay. I don't know what it is in radians. For B, R is root R is 5 for all of them. Yeah. So, on the second one, I'm not going to labour this point too much in a minute because I'm going to show you how your calculators will handle all this. Are you listening? On the second one, what you've found is this angle in here I've called alpha, 53.13 degrees again. But what we're interested in is this angle in here from 0. So the angle here actually equals, I've got to call it alpha. Is 180 degrees minus 53.13 degrees, which is 126.87. So minus 3 plus 4j equals angle 126.87 degrees. And then the other two, C, again, that's 5, and the angle is minus 126.87. Yeah. And D, you should get 5 angle minus 53.13. Sorry? Yeah. Yeah, you'll get as a negative angle, but what you're looking at is all you're interested in is the size of it to take away from 180 anyway. Yeah, I'm going to show you how to handle all this conversion and calculate in a minute, so I won't worry too much about it. But you're actually finding with the tangent the minus 1 function, you're finding that angle in there, and all you've got to do is take it away from 180 to get this angle in here. So you're not really interested in it being minus or plus. Alright? So that's conversion from rectangular to polar form. And then what we're going to do now is just have a look at a couple of examples of going the other way from polar form into rectangular form. So we've got this example here of 4 angle 30 degrees. How can I find the real part? X. I'm going to convert that to rectangular. So how can I find X? Tangent is opposite side over adjacent side. It's not tangent, remember? So which ratio do we need to use to find X for the information we've got? We want to find the adjacent, we've got the angle, and we've got the hypotenuse. Cosine, yeah? Cos 30 is equal to X over 4. Therefore, X is equal to 4 cos 30 degrees. Four significant figures, please. What is it? Yep. And then, therefore, how do I find y? Opposite side, hypotenuse. All lost your tongues this morning? Sine. Sine 30 degrees is equal to y over 4. Therefore, y is equal to 4 sine 30 degrees equals, and again, 4 significant figures, please. Four significant figures. 2. All right. So this one is therefore in rectangular form. It is 3.6464 plus 2j. What about this one? What angle are we going to have to know to be able to solve that one? We've got a vector over here in the third quadrant. Yeah, it's going to be alpha is 180 minus 145 equals 35 degrees. Yeah. Then we can go x is 7 cos 30 degrees. Sorry. And y is 7 sine 30 degrees. Four sig fig, please. Who is that? Come on, what is it? On the Richter scale, I think. Okay, so what is the full form, rectangular form of that angle? You're wrong. Right, can you pack it in now, please? Right? How do we write? What did you just say, Macaulay? I know what you said. You said 5.734. What did you say? Plus 4.015J. Right. It is wrong. What's wrong with it? You tell me. Look, this is in the third quadrant, so it should be a negative imaginary part and a negative real part. All right? Okay? So, that's how you convert, if you haven't got the right calculator, between rectangular and polar form. Alright? Now, what I'm now going to show you to use your calculator, I know for Casio calculators. If you've got a Sharp, then that may well do the same thing in some way, but I don't know how. Right? So, use of calculator to convert between polar and Cartesian forms. Modern calculator can achieve the conversion between the two forms. This will be needed for polar complex numbers to be added and to convert Cartesian or rectangular form in a proper vector of magnitude. Because what we're in engineering problems, what we're going to be interested in, particularly mostly for the final answer, is that we have it in polar form, magnitude and angle. Yeah. So most of the time, we may there are a couple of topics where you want to separate the horizontal component and the vertical component, but normally you're interested in the final answer being in polar form. Right. So, if you put your calculator in radians mode first, please, because that's what these problems are in. So the first one there is converting 6 angle 1.23 radians into Cartesian form. You push the shift button. You push rec, which I believe is on the Casio calculator on the minus button. And then you put in 6, which is the magnitude of the polar number. So when you want to know which to push, you push the form that you want to convert to. So we've gone from polar to rectangular. Then we put a 6 in. Your calculator will open up a set of brackets in here, by the way. So your calculator will open up. Then you push the shift key, and this little dash is on your close brackets button. And then you put in 1.23, which is your argument or angle. That can be negative. You can put a calculation in these positions as well. So you can put 6 plus 3 in there if you want to. There can be a calculation or fractions in the 1.23 bit. Close the button, push the equal sign. What you'll get is an x value, which is your real part. Hang on, I'll help in a minute. So you'll get a... Go away. You'll get a real part as x and an imaginary part as y, which you can interpret as 0.005 plus 5.655j to 4 significant figures. Yeah? And then, to go the other way, to convert 4 minus 2j to polar form, Similar thing, shift, but you push polar, put the 4 in, can be negative, can be a calculation in there, that comma thing, and then a -2, close the brackets and equals. Okay, this method will handle all that business about which quadrant it's in, and it will give you negative angles in the bottom 2 quadrants, positive angles in the top 2 quadrants, all automatically, as long as you enter it right. Here we get an R value, 4.472, and a argument in radians or degrees, depending on what mode you got your calculator in. Alright, so I'm going to come round now and see if I can help make sure you can all do that. Taylor, if it's not obvious on your sharp calculator. Have you found out how to do it then? I'll try, but I don't. Right, boys. So, addition and subtraction of polar complex numbers. Now, it can be done manually, but it requires some tricky knowledge of geometry. You really need to draw a diagram and then use the sine and cosine rules. Okay, so when we have 2 or more polar numbers that we want to add or subtract, what we're going to do is convert them to Cartesian form first, and then we can easily add those together. So with your newly armed skills, and with the here we got our angles in degrees, so you need to switch back to degrees mode, convert those 3 numbers to rectangular form. Yeah, that's what I'd like to use, something like that to express what you're doing. And then 5 angle minus 45 degrees. We're going to add those 2 together. And then afterwards we're going to subtract well, actually what we can do, something to watch here, we can add -4 angle 120 degrees. So what do we get for the second one then? 5 angle minus 45. Plus or minus? Minus. Should be. Did you put minus 45 degrees in for the angle? Minus. Yeah, the Y is minus. Right. And the 4 angle 120. Yep. So now we got how do we add 2 complex numbers together in rectangular form? No, do we? Done that last week. Who said, hang on. What does that come out as? Leave the minus out of there. What do you get? Yeah, you do. Look, 120 degrees is in that quadrant. Negative real part, positive J part. Minus 2 plus 3.464J. Yeah, that's what you got. Now we've got to add these two together. From last week, how do we add two rectangular complex numbers together? So, if we have one, two or more polar form numbers to add or subtract, what we do is use our calculator to convert them to rectangular form, add them together, subtract them separately, like you all know we need to do now. Okay, and then when you got the final answer, in this case 7.268 minus 6J, convert back to polar, what do we get, gents? That ain't what I got here. I got 9.425 and I got 39.54, but you didn't put the minus 6 in, yeah? So that's minus 39.54. Yeah? And this is where it's useful to be able to think about what quadrant that rectangular number is in. That's got a positive real part, negative J part. It must be down in the fourth quadrant. Yeah? Positive real part, negative J part. Must be somewhere in here. So we should get a negative angle between 0 and 90. Helps you to twig whether you got your calculations wrong, whether you missed that negative sign out in the conversion. Alright? Because your calculator from these conversions will give you positive results in quadrants 1 and 2. Yeah. Between 0 and 90 in quadrant 1, between 90 and 180 in quadrant 2, and that will give you negative angle results in the third and fourth quarters. Alright? So on your remaining page in your handouts, there are some problems to evaluate in polar form. So you can have a go at them now. And I've got some answers if you want to know whether you're right or not. Okay? Multiply two polar complex numbers together. I'll pick anything at random. So what we're going to do is 5 angle 40 degrees. I like to put them in brackets when I do this multiplication. Multiplied by 6 angle minus 32 degrees. Okay? What we do is multiply the magnitudes, add the angles separately. So here the answer is 5 times 6, angle 40 plus minus 32. You just need to be careful with negative, positive, negative again. Alright, so the answer here is 30, 5 times 6 is 30, angle 40 plus minus 32 is 8 degrees. So to multiply, it's the easiest one of the lot, these really. To multiply, we multiply the two magnitudes together and we add the two angles. Right? And you get the same answer if you've done 6 angle minus 32 times 5 angle 40. You can do them in either order. Okay? Yeah. And then one more page. We'll do we'll do 6 angle 40 degrees divided by 3 angle minus 25 degrees. Yeah, here we divide the numerator magnitude by the denominator magnitude. And we subtract the denominator angle from the numerator angle. Notice that with division, the order is important. Okay, so in this case, the answer is 6/3 angle 40 minus 25. Again, care with positive negative signs. 6/3 is 2, angle 40 minus 25 is 65 degrees. Yeah. There. If you just hang on a minute, you can finish off. I'll leave it up there. Just in summary then, guys, add and subtract complex numbers. We need to put them in rectangular form. Yeah, I haven't even shown you how to do add and subtract polar numbers directly in polar form. So you need to, if you're going to add or subtract any polar numbers, you're going to convert them to rectangular and then back again if need be. Okay? If you're multiplying and dividing, unless you're specifically asked to do it in rectangular form, you're better off convert to polar and then back again if need be, because it's easier. So multiply and divide is easiest in polar form, add and subtract is easiest in rectangular form. Alright? I may, however, depending on what I got to assess you on, have to ask you to do some multiplication in rectangular form, division. But unless you're specifically asked, You may use this conversion, but please explain to me what you're doing, how I've done it with a similar notation with the arrow and say I'm converting from one form to another with the calculator. All right? Be careful about having it in the right mode, radians or degrees. Everybody happy with that? Yeah. And these notes from the board will go up on Moodle, all right?